Good day, viewers all over the world. I welcome you to today's class. It has been a great time with you. I want to first of all appreciate every one of you that have been watching my videos, and I want to also appreciate all those who have subscribed to my YouTube channel. May God bless you on every side. Today we shall be looking at a special topic that is titled Stability, Convergence, and Consistency Analysis of an Explicit Two-Stage Second-Order Runge-Kutta Method. Beloved, please, if you have not yet subscribed to my YouTube channel, subscribe to my YouTube channel, Dr. Chris Esekaigbe. Click on the notification button so that anytime I upload a new video, you will have a notification. Like my videos, share them in your social media platforms, and as you do, God will bless you. The essence of this YouTube channel is to share knowledge in key areas in mathematics and statistics, numerical analysis and applied statistics preferably. My name is Dr. Chris Esekaigbe. I am a chief lecturer in one of the most prestigious polytechnics here in Nigeria. I hold a doctorate degree in mathematics with distinction, a master's degree in mathematics, and a bachelor degree in statistics. I am a specialist in numerical analysis, data analysis and modeling, and also applied statistics. Please, if you are a research firm or an AI firm, you do a lot of artificial intelligence, you train AI models with mathematical algorithms, why not you can contact me to be part of what you are doing. I've been privileged to work with one or two firms in the US, helping them to train AI models. I'll be expecting a call from you, or you are a research student, you need my assistance in the area of numerical analysis and applied statistics. Why not? You can contact me. My contacts are +234 80 330 21903. This first contact is for call and WhatsApp. Then the second contact is +234 7066 297535. This second contact is only for call, it's not for WhatsApp. Then my email address is chrisdavid2015@gmail.com. I'll be expecting to hear from you. Watch my videos, share them in your social media platforms, and if you have not subscribed, please do so, and God bless you. Permit me to go into the business of the day. Numerical methods are approximate methods that help us in getting solutions to real-life problems, especially when conventional methods are not able to do so. Numerical methods are highly efficient. They are highly reliable. The Runge-Kutta method is one of the one-step methods that is used for solving initial value problems in ordinary differential equations. We have implicit Runge-Kutta methods, we have explicit Runge-Kutta methods. And the first of all is the second order two-stage method. In our last video, I used the two-stage second order method to solve an initial value problem, and we compared the result with the theoretical solution, and we found out that the two-stage second order method is highly efficient and capable enough in handling initial value problems. Now, for you to determine the reliability of a numerical method to use, you have to test or prove that method. There are certain criteria or certain properties that such a method must possess. There are certain criteria and certain properties that such a numerical method must possess. Be it Runge-Kutta method, whatever numerical method, it must satisfy these properties before they can be capable enough to handle the problems that they were developed or derived to handle. One of such properties is stability, another one is convergence, and another one is consistency. The method must be consistent, the method must be convergent, and the method must be stable. So we are going to look at these three proofs today. We want to test if this numerical method, this second order two-stage Runge-Kutta method, whether it is stable, whether it is consistent, and also whether it is convergent. Now the first thing we are going to do, we are going to look at the proof for stability. Let's start with stability proof. This is the second order two-stage Runge-Kutta method. You can see it. It has two stage, K1, K2, two stage. Then it's a second order method. Now let us look at proof for stability. Now, for you to prove that a Runge-Kutta method is absolutely stable, there is a test equation that is normally used. The test equation that is normally used for such proof is y prime equals lambda y. This is our test equation that we normally use to prove if a Runge-Kutta method is absolutely stable. And there is a stability polynomial function that is expected that you must arrive at depending on the order, depending on the number of stages, and depending on the order. As I said, the order is of order P. So having this test equation, this is the test equation we normally use to prove the stability of a Runge-Kutta method. And again, the initial value problem that we normally solve is of the form y prime equals f of x subscript n yn, then y of x naught is equal to y naught. So this is the nature of the initial value problem that we solve. So from the proof has already started. Just watch patiently to the end of the video. At the end of the video, you will be able to know how to prove the stability of a Runge-Kutta method. If peradventure you are a postgraduate student or even an undergraduate student, you want to specialize in numerical analysis. I am a specialist in numerical methods. I got my PhD in numerical methods. If you derive any Runge-Kutta method or any numerical method, it is good to test for these properties. If the method is stable, the stability of the method determines the performance of the method. The consistency of the method determines the performance of the method, and the convergence of that method also determines the performance of that method. So after deriving any method, be it Runge-Kutta method or any other numerical method, it is good to test for stability, test for consistency, and test for convergence. It is very, very important. If the method is stable, if the method is consistent, and the method is convergent, then you are sure of that particular method generating the desired result. So now, this is the second order two-stage Runge-Kutta method. This is the test equation we normally use to prove for stability, and this is the nature of the initial value problem that the method is expected to solve. Now, from this particular method, you will see that from the Runge-Kutta method above, look at it, our K1, K subscript 1 equals to f of xn, yn. Look at it, it's very simple. Then look at here now, our y prime from this particular problem is also f of xn, yn. So that means marrying these two together or connecting these two equations together, it means that our K1 is equal to y prime. And what is y prime from this key equation? Our y prime is lambda y. So this simply means that our K1 is equal to lambda y. Our K1 is equal to lambda y. So that is the first fact we have to establish. So having that, we can also impute this into K2. So if our K1 is lambda y, we can get our K2 from here. Our K2 will be equal to, our K2 will now be equal to lambda into, look at it here now, you have your y plus, what is our, this is our y plus h K1. Now what is our K1? Our K1 is lambda y. So it will be h lambda y. That is what our K2 will be. So our K2 will be lambda into, you have the y, look at the K2 here, you have the y plus h. Now you are substituting the value of K1 to be equal to lambda y. You put it here, lambda y. So our K2 will be equal to lambda into y plus h lambda y. If you have K3, you keep going in like that. You substitute K1 and K2 into K3. If you have K4, you substitute K1, K2, K3 into K4. If you have K5, you substitute K1, K2, K3, K4 into K5. It keeps going on like that. You keep on substituting these values into that so that you can have what you want to derive. So having gotten this, we are now coming here to write our key equation. Look at our key equation here from the second order two-stage method. We now have it as our, you can bring this y n back. So you now have your y n plus 1 minus y n is equal to, you now have your h over 2 bracket. What is our K1? Our K1 is lambda y plus, what is our K2? Look at our K2 here. Our K2 is lambda into y plus h lambda y. You close this bracket to this, then to this one, you close the bigger bracket. That is how it is done. So, having done that, you are now going to expand. You come here and have your yn plus 1 minus yn, that is y subscript n, will be equal to h all over 2, bracket open, lambda y. Then we need to open that other bracket, lambda times y will be plus lambda y, then plus lambda times h square, lambda times h lambda y will be h lambda square y, then you cover the bigger bracket. You can see we are making good progress. Then having done that, you take the like terms, you add the like terms together. You have your yn plus 1 minus yn will be equal to h over 2 into 2 lambda y plus lambda y will be 2 lambda y, then plus h lambda square y. Then if you continue, you have yn plus 1 minus yn is equal to h over 2. Then what is common there? You have lambda y common, so you bring it out. You have lambda y into 2 will be left here. 2 plus, if you bring lambda y out, you have h and you have lambda left. That is what you are going to have. So having that, you're now going to divide all through by y and set mu equals lambda h. So dividing all through by y, divide all through, you divide all through by y, divide all through by y, comma, set mu equals lambda h. Lambda h. So doing that, you are going to have yn plus 1 minus yn all over y. We are dividing by y. Then you also divide the right hand side by y. You are coming here, you are going to have it as equal to, you are going to have h lambda y all over, of course, 2y, and bracket open, 2 plus h lambda. Note we are coming to set mu to h lambda plus, let's divide first. Now you are going to have yn plus 1 over y minus 1. When you use yn to divide yn, you have 1. Then, of course, y will cancel y. This will now be equal to h lambda over 2. Then, bracket open 2. Of course, okay, we can open the bracket right away. Let's open the bracket right away. Lambda, we have h lambda over 2 multiplied by 2. So you are going to have 2. You are going to have 2h lambda all over 2 plus okay, let's have it this way. Let me not jump any steps so that it will be easier. So you are going to have h lambda over 2 bracket 2 plus, okay, let's just put the mu directly since we are setting h lambda to mu. So it will be mu over 2 plus, it will be mu over 2 bracket open 2 plus mu. So you close it like that. Since our h lambda is mu, so we can accept this one like this. You are going to have mu, you are going to have mu over 2 bracket open 2 plus mu. So at the end of the day, you come here, you are going to have yn plus 1 all over y will now be equal to 1. You take this one to the other side, then you are going to have plus 2 mu over 2 plus mu square, mu times mu is mu square all over 2. So these two, we cancel these two. So this will now result to 1 plus mu square all over 2. That is now the stability polynomial function. You can see how this has been derived. I hope there is no confusion along the way. Let me come again. You divide all through by y. So this side, the left hand side, you divide by y. Then of course the right hand side you also divide by y. So this will be h multiplied by lambda y will be h lambda y all over 2. Because we are dividing by y, it will now be 2y. Y will cancel y. Then you now have 2 plus h lambda. Remember we are setting our mu to be lambda h. So you come here, anywhere you see lambda h or h lambda, you put your mu. Here we are having h lambda left, that's why we put our mu there. So h lambda is mu all over 2. Then now you come and open the bracket. This minus 1, definitely yn over yn is 1. Then you now have yn plus 1 over y or y subscript n. So you take the 1 to the other side, minus 1, when it crosses to the other side of the equation, it becomes plus 1 plus, you now open this bracket, mu times 2 will be 2 mu over 2. Mu over 2 times mu will be mu square over 2. So 2 we cancel 2. You have this one here. 2 we cancel 2. You have mu. Then mu square all over 2. So now the polynomial, the stability polynomial function will now be written as r of z is equal to 1 plus mu squared over 2, and that is equal to 0, normally equated to 0. So this is the stability polynomial for the second order two-stage Runge-Kutta method. Now there is a general polynomial equation that is expected. It is written as 1 plus mu squared over 2 factorial plus mu raised to power 3 over 3 factorial. You can start to put factorial here because 2 factorial is the same thing as 2. So it is always put in factorial. So if the normal stability polynomial equation for whether implicit or explicit Runge-Kutta method is this polynomial 1 plus mu square over 2 factorial plus mu raised to power 3. If the order is over 3, order 3, you will have mu raised to power 3 over 3 factorial. If the order is order 4, you will have mu raised to power 4 over 4 factorial. 4 factorial is 24. 3 factorial is 6. If the order is of order 5, it will be mu, it continues to mu raised to power 5 over 5 factorial. So where this polynomial stops is dependent on the order, because this order is of order 2. That is why it is stopping at mu raised to power 2 over 2 factorial. If it is of order 3, it will stop at, there will be another 10 there plus mu raised to power 3 over 3 factorial. But because it is of order 2, it is stopping here. And note, the stage is also put into consideration. The stage here is 2. For implicit Runge-Kutta method, you will use this stability polynomial function. You will arrive at this, but for the implicit Runge-Kutta method, the stage determines where it stops. The stage, you will see implicit Runge-Kutta method of order 4, stage 2. You will see of order 4, stage 4. You will see of order 4, stage 3, and so on and so forth. So the stage determines where the polynomial stops. It is like that. So this is the proof for stability. We have gotten the stability function or the polynomial function for the two-stage second order Runge-Kutta method. Now, permit me to go for test for convergence. Now, we are going to use the initial value problem to test for convergence. If the method, the two-stage second order Runge-Kutta method, if it converges to the initial value problem, then the method is said to be consistent. So permit me to claim this proof for stability. I hope you have written it out, you have studied it, so that you study it. If there is any question, please put it in the comment section. It will be attended to. If you have any query or any question or any part you want me to explain further, you can put it in the comment section. I will definitely get back to you on that. So that is the proof for stability for this second order two-stage Runge-Kutta method. Now permit me to go for the proof for convergence. Proof for convergence. Proof for... Now that we just finished the proof for stability, it is time for us to test for convergence. We want to test for convergence of this second order, second stage Runge-Kutta method. We want to see if the method will converge to the initial value problem. And if the Runge-Kutta method converges to the initial value problem, of course, we can say that the method is consistent. Remember, our IVP, the initial value problem, the IVP is y prime equals f of x subscript n, comma y subscript n, comma y of x naught is equal to y naught. That is our initial value problem. Now, the first thing to do is to bring out the key equation from the problem. Yeah, now the proof. The first thing bring out the key equation. The key equation from the model, the second stage, second order Runge-Kutta method, the explicit method. Now we want to bring out the key equation. The key equation, which is the increasing equation, we have to bring it out, and it's going to be y subscript n plus 1. Of course, take this other side to the left hand side, yn, that will be equal to h all over 2 into k1 plus k2. So that is the first step in this proof. Now, the next step is to write k1 and k2. Write k1 and k2 in terms of f of xn, yn only. So now, of course, our k1 is already in that format, which is f of xn, yn. Then, of course, our k2 will not be equal to, so of course we have to insert the value of k1 into k2. So k2 will be f into xn plus h, yn plus h. Of course, our k1 is f of xn, yn. You cover the bracket. Of course, there's a bigger bracket to cover. Now, having done that, our next step is to insert k1 and k2, this new k1 and k2, into the key equation. So insert k1 and k2 into the key equation. So doing that, permit me to share the board into two parts. Doing that, we'll now come and have our yn plus 1 minus yn equals, of course, we have our h over 2, bracket open. Of course, we have our k1 first. This is the key equation. You can call it the star equation. Of course, we have k1 first. Our k1 is f of xn, yn. Then, of course, our k2 is this. Of course, let's put a plus sign there. F into, we are now writing out k2, xn plus h, 1n plus h, f of xn, yn. You cover this bracket for this. Then there is another bracket here to cover. Then a bigger one to be covered. So that is how it goes, like that. So now, having done this, we have to first of all divide both sides of the equation by h. Dividing both sides by h, divide both sides by h. So we now have yn plus 1 minus yn all over h is equal to h all over 2 h, because we are divided by h, so that will come. Then we now have bracket open f into xn, yn, which is that, then plus, of course, f into xn plus h, yn plus h, f into xn, yn. This bracket close, then covering this other bracket, then covering the bigger bracket. Of course, you will see this h here, we cancel this h. So we are now going to have, the next step is taking limits of both sides as h approaches 0. We have, so you can see that we can take the limit of both sides. So now this will now be limit as h tends to 0. we have yn plus 1 minus yn all over h. You see that there? This will now be equal to, now you are taking limit as h tends to 0. Listen to this very carefully. H has cancelled h. You are now taking limit also as h tends to 0. Of course, this is 1 all over h. 1 all over 2. Because h has cancelled h. Of course, you open the bracket, you have f of xn comma yn. Then, of course, plus this one is here, f of xn plus h comma yn plus h, f of xn yn, bracket close, bracket close, bracket close. Now, taking this limit, as we take this limit as h tends to 0, you have y subscript n plus 1 minus y subscript n all over h. We are taking the limit of it. This is not n, this is h. Then you close. This will now be equal to, now look at it as h tends to 0. You have 1 all over 2. Now bracket open. There is no h in this first one, so you put your f of xn comma yn. Then of course this plus sign, you put it here. Now as h tends to 0, this h tends to 0 here, so this will be xn plus 0. Of course there is a comma, so you have your f of xn comma, which is this one, f of xn, the h as tends to 0. Of course there is a yn here, you put the yn. Now look at it now, there is an h here, everything here. This h tends to 0, multiplying everything here will be 0. So this one will now close. Then of course, you now have a bigger bracket, so it has reduced to this. So taking this limit, this will now be equal to 1 all over 2, bracket open, 2, f of xn comma yn is n, not h, f of xn comma yn, and then plus f of xn comma yn, you have 2 of f of xn comma yn. So you see that these two will now cancel these two. So when you now come now, you will now see that when you now take the limit as h tends to 0 of yn plus 1 minus yn all over h, it has now reduced to the initial value problem, which is f of xn comma yn. You can see that the particular method has now converged to the initial value problem. You can see the initial value problem. Look at it here. That is what you have there. So the method has converged to the initial value problem. So it is important you know that the method reduces. It has reduced to the original initial value problem in the limit. You see it in the limit as h tends to 0. So this satisfies the consistency condition. It satisfies the consistency condition. So if it converges, if the limiting equation converges to the initial value problem, then the condition for consistency is satisfied. So this leads us to a particular definition which says a numerical method is said to be consistent. A numerical method is said to be consistent if its local truncation error tends to 0 as h tends to 0. So a numerical method is consistent. So if the local truncation error tends to 0 as h tends to 0, then a numerical method is consistent. So you can see that. So we have been able to carry out this proof. You can see that in conclusion, the two-stage second order Runge-Kutta method is stable, is convergent, and is also consistent. Remember, don't forget that definition. A numerical method is said to be consistent if its local truncation error tends to 0 as the mesh size or the step length h tends to 0, and also if the method reduces to the original initial value problem in the limit as h tends to 0, then that particular method is said to have satisfied the consistency condition. Beloved, we have come to the end of this class. I believe you have seen how we can test for stability, convergence, and consistency of a second order, second stage, or probably two-stage Runge-Kutta method. This is also applicable for other Runge-Kutta methods. It can be 3-stage, it can be 4-stage, it can be 3 or third order, fourth order, whichever stage. This is just how we test for consistency and convergence. It's nice having you in class today. I believe you waited patiently to watch the video to the end. If you have not subscribed to my YouTube channel, please subscribe. And if you have subscribed, I appreciate it. Continue to share my videos in your social media platforms. Share them, like the videos, click on the notification button if you have not subscribed, and subscribe, and God will bless you. The essence of this channel is to share knowledge in key areas in mathematics across the globe. And as you do that, God will bless you. Enjoy the rest of the day. Bye. See you in our next class.